here we have got a typical example of this concurrency versus parallelism. So, if we have got a single core system, then these tasks T1, T2, T3 and T4. So, these are various tasks that we have in the system, and over the time the scheduler schedules the tasks in this fashion, that first it schedules T1 for some time quantum, after that it schedules T2 for some time, then T3 for some time, then T4 for some time, then again it picks up T1 for execution. So, this type of execution we will see later. So, this is known as round robin type of scheduling. So, each task is given CPU for some small amount of time. So, this is a concurrent situation because all the tasks, so they are progressing. So, if you look into the task at some point of time, so all the tasks, so you will see that okay, T1 has progressed to some extent, T2 has also progressed to some extent, T3 has also progressed to some extent. So, like that, maybe the amount of progress is not uniform across all the tasks, but all of them are progressing. It is not that T1 is executing and all of them have not done. So, T1 is just finished and none of the others they could execute even some small fraction. So, that will not be the situation. So, this way this scheduler it can be used to have concurrency in a single core system. On a multi core system, so we have got say 2 cores, core 1 and core 2. Now, the job of the scheduler is more complex. So, it has to decide not only which job to execute next, but onto which core. So, there are issues in this multi core scheduler design. So, for a typical case may be like this, that in core 1 it first on core 1 it puts the odd numbered jobs, and on core 2 it puts the even numbered jobs. So, this is a totally hypothetical decision that the scheduler has taken. So, this T1 is run for some time, then it is given to T3, then T3 runs for some time, then again given to T1. So, it goes like this. And similarly for core 2, first T2 runs for some time, then T4 for some time. Now, whether it is a good or bad distribution of this task to core, so that is that can only be answered when we see the total finish time for all the tasks which are constituting the whole application for this. So, it may so happen that we need to take a much better decision, and this may be turn out to be a very bad decision, because T2 and T4 those tasks may be quite small compared to T1 and T3. So, as a result this second core will remain idle for a good amount of time, and that has to be reduced. So, if we are trying to optimize the performance. So, this parallel, so we get parallelism in here because this T1 and T2 they are progressing parallelly, T3, T4 they are progressing parallelly, and we also have concurrency because at any point of time all the tasks, so they have executed up to some point. So, that way we have got both parallelism and concurrency in multi-core system. Now, if we increase the number of cores, then how does this performance improve? Okay. So, this is we ideally we would like to have a situation like if I instead of using one core, so if I use 2 cores, then my performance throughput should be double of the previous one, because per unit time I can do 2 jobs which can be which is possible by a single processor. So, that way that is the expectation, but unfortunately if you look into any program, then entire part of it cannot be done parallelly. Okay, there will be some part of it which is inherently sequential. So, you cannot do any parallelization of that, and there are some portion which can be parallelized. So, only the portions which can parallelized, so they can be given to this parallel jobs, parallel cores, and that way you can get performance improvement. So, this is the Amdahl's law. It says that identifies performance gains from adding additional cores to an application that has both serial and parallel components. So, a job with a task can have, an application can have both serial and parallel components, because initially it may be doing some operations, and only when it comes to some sort of say array updation and all. So, for I equal to 1 to 1000. So, A I equal to B I plus C I. So, something like this. So, then I have got parallelism, but as long as it is doing operations like say x equal to y plus z, then p equal to x into k. So, like that. So, I cannot have parallelism, because this x value So, these two statements cannot be executed in parallel because this x is just computed here. So, I cannot do them in parallel. So, this way some part of the code is inherently sequential. So, you cannot do parallelization, and there are some parts of the code so which can be very easily parallelized. So, this Amdahl's law says that if I have got n processing cores and S is the serial portion, then the speed up will be less or equal 1 upon S plus 1 minus S into n. So, for example, suppose we have got an application where 75% is parallel and 25% is serial. Now, if I have got a single core, then I have got S. So, S equal to 75% is parallel, 25% is parallel. So, S equal to 0.25, and this for a single processor system n is equal to 1. So, this expression becomes 1 upon 0.25 plus 1 minus S, that is 0.75 divided by 1, n equal to 1. So, this gives me equal to 1. The speed up is equal to 1. So, if I have got single processor system, then with respect to single processor system there is no improvement. Now, suppose I put 2 cores. So, n is equal to 2. Now, what will happen? So, this expression value becomes 1 by 0.25 plus, so 0.75 divided by 2, and then so this value, so it is 0.75 by 2. So, this is 0.375. So, 0.375 plus 0.25. So, that will make 0.625. So, 1 upon 0.625. So, this is about 1.6. So, this is equal to 1.6. So, what happens is that, so that means if you go from one processor to 2 processor and the code is such that it is 75% parallel and 25% serial. Okay. So, then you can get a speed improvement of 1.6 only. Now, you see if you look into this expression carefully, so it says that, so this is the serial portion. So, this I cannot do anything here, and this 1 minus S is the parallel portion. So, if you are having more number of processors, so this time will reduce by a factor of n, theoretically of course. So, this is not the practical thing. So, this is theoretical, because practically there will be time for communication, there will be time for data distribution and all that. So, they are not taken care of here. So, assuming that everything those timings are 0. So, this is S plus 1 minus S by n. So, this part gives me the speed up. So, this to look into these possible values of this S of this speed up, when n approaches infinity, then this term is almost 0. So, the speed up becomes 1 by S. So, if you have got infinitely many number of processors, then the speed up will be given by 1 by S. So, as you can see that the serial portion of an application has disproportionate effect on the performance gain by adding additional cores. So, if you add additional cores, so even if I add infinite number of cores also, then the speed up will be 1 by S. So, if the sequential portion is more, then naturally speed up will be less. So, if a program is 100% sequential program, then even if you put say infinite number of cores, the speed up will remain 1 only. So, that is the idea of this Amdahl's law. So, how does this law take into account the contemporary multi-core systems? So, contemporary multi-core systems are much more complex. So, naturally this is a theoretical study, and this may not be able to give a true picture there, but this gives the theoretical upper limit on the degree of speed up that you can achieve. So, next we will have a look at a graph that shows that, okay, so this is the ideal situation. So, as you are increasing number of processors, then the speed up should grow like this. So, this red line, so with 1 the speed up is 1, with 2 the speed up should be 2, with 4 the speed up should be 4. So, it should grow like this. On the other hand, ideally what happens is as the sequential portion increases. So, this graph is not coming fully. So, as the sequential portion increases, this speed up starts decreasing. Okay. So, these are as you go down, the speed up, the sequential portion is more, as a result this improvement becomes poor. So, that is the graphical interpretation of this Amdahl's law. Next, looking into the types of parallelism that we have. So, we can have data parallelism. So, data parallelism, the focus is on distributing subsets of same data across multiple computing cores and performing the same operation on each core. So, the same data is the data has to be distributed. So, the same operation will be done on the different data. For example, if you have to sum the contents of an array of size n, then on a single core system we can have one thread to add that would sum the element 0 to n minus 1. So, assuming that array indices run from 0 to n minus 1. So, on a single core system I can have one thread that does the addition for all these n entries in the array. On a dual core system we can have thread A running on core 0 that could sum 0 to n by 2, while thread B running on core 1 could sum n by 2 to n minus 1, and then after that I can do the addition of these two partial sums by using again maybe core A or core B, either of them. The two threads would be running in parallel on separate computing cores. So, that way once I have distributed the data, so 0 to n by 2 to core 1, and so 0 to sorry, this should be n by 2 minus 1, this is not n by 2. So, 0 to n by 2 minus 1 to core A, and n by 2 to n minus 1 to core B. Once we have done the distribution, after that I give the same instruction for both the cores, telling that you add all the numbers that you have. So, after that they come up with the partial sums, and then using another addition. So, I have to do that. So, that way we have got this thread level data parallelism. On the other hand, we can have task parallelism also, that involves distributing not data tasks, not data, but tasks across the multiple computing cores. Each thread is performing a unique operation, and different threads may be on operating operating on the same data, or they may be operating on different data. So, different tasks are given to different threads. Okay. So, that is the task level parallelism. So, this we have like previously I was telling, for the same matrix you may be interested to find the transpose of the matrix, inverse of the matrix, and determinant of the matrix. So, like that. So, they can, so I can define the same matrix can be given to a number of tasks. So, we can and each task may be doing one of these operations. So, that way you can have task level parallelism there. Next, so this is the situation. So, in a data level parallelism, so we have got this the data is divided into portions, and each core is given the part of the data. So, core 0 is doing for this part, core 1 is doing for this part. So, the instruction is same across all the cores. Whereas, the task level parallelism, so data maybe the same data is given to individual all the cores, or maybe different data are given to different cores. So, both of them are possible, but the operations that they are doing are all separate. So, that way we have got this task level parallelism. So, this individual cores, so they are doing different tasks, but the data may be same or data may be different. So, that is the task level parallelism. Now, coming back to the discussion on operating system. So, we can think about the operating system when it is executing the processes. So, we have seen that the process may have multiple threads. Now, we also know that when a process is executing, so there are two modes of execution. For some time it executes in the user mode, and sometimes it executes in the kernel mode. So, normal computational jobs when it is doing, so it is executing in the user mode. Whenever it is doing a system call, so it is going to the kernel mode. Now, So, at both user level and kernel level we can think about multiple tasks that can go simultaneously. So, maybe at user level I have got say 3 different tasks that should go parallelly. So, I can have 3 different user level threads that takes care of that. Similarly, at kernel level also I can have multiple such tasks going on parallelly. So, I can think about kernel level threads also. So, this support for threads may be provided at both the user level and kernel level. So, we have got user threads that are supported above the kernel and are managed without kernel support primarily by user level threads libraries. So, we have at user level threads libraries are there. So, using those library calls, so we create different threads and those threads are they execute in parallel, but they are not making any system call. So, none of them are going to kernel mode of execution. On the other hand, these kernel threads they are supported by and managed directly by the operating system. So, as an operating system designer, so we have to provide these kernel threads and we have to tell interface for those kernel threads, like whenever a system call is made. So, we do not need to tell the user like how the system call is going to be mapped onto threads at the kernel level, but the interface like how this system call will be made. So, up to that much is sufficient. But at the implementation level, the operating system designer may think that I will have multiple threads in the kernel, and when a particular system call is being called, so how this is going to be mapped onto the kernel level threads there. So, at user level, so it is handled by thread libraries. At kernel level, it is handled by the operating system. So, virtually all contemporary systems support kernel threads. So, we have got Windows, Linux, Mac OS X. So, all these operating systems, so they will support kernel level threads. So, we will see how these things are actually taking place. So, there can be different types of relationship between the user and kernel threads. There are three very common ways of establishing relationship, like many to one, one to one, and many to many. So, between the user level threads and kernel level threads, how this mapping will be or the relationship will be there. So, just like many other type of mapping that we have in different domains. So, how is it taking place in case of threads? So, that is that we will see, and the first one is the most simple one is the one to one model. So, in one to one model, what happens is that each user level thread maps into a single kernel thread. So, creating a user level thread also creates a kernel thread. So, whenever a user thread is created, suppose a new thread is created here. So, accordingly a new kernel thread will also be created, and this thread will be mapped onto this. Similarly, this thread is mapped onto this thread is mapped onto this thread is similarly there should be another thread onto which this will be mapped. So, whenever you create a new thread in the user space, a new thread is created in the kernel mode also. So, each user level thread maps to a single kernel thread. So, creating a user level thread creates a kernel thread as well. So, more concurrency than many to one, because what happens is that if this thread makes a system call, then this thread will be taking care of that, or if this thread makes a system call, so this thread will take care of that. So, for every user level thread I have got a kernel level thread which will be taking care of that. So, whether it is good or bad, so it is good because I do not be bothered about whether some other thread got blocked or not. So, if this thread got blocked here, okay, it cannot proceed. So, other threads will not suffer because of that, because they have got their own thread. So, it is restricted to that particular operation only or that particular thread only. So, this whole thread may be blocked, but that will not make others to wait. So, this is better in the sense that we have got more concurrency than many to one, but the difficulty is that we are creating large number of threads. So, as and when a user thread is created, one kernel thread is also getting created. So, that way if the user program does not make a good number of system calls, then this kernel level threads, so they will be mostly unutilized. Okay. So, that way it is not a very wise decision to create so many kernel level threads, and that the system resources are blocked because of that. So, number of so you have got more concurrency, but number of threads per process has to be restricted, like one process may go on creating threads, user level threads, and as a result for each of them it will create some kernel level threads also. And since the program that we have, so program is written by some user who may or may not be very good in this thread level programming, maybe by mistake the user creates an infinite loop, and in that infinite loop it creates some threads. So, as a result at the kernel level also infinite number of threads will get created. So, that is a very dangerous situation for the system. So, operating system designers, what they do, they often put an over restriction and on the number of threads, kernel level threads that you can create, or number of threads that you can create per process. So, this to restrict this overhead. So, typical examples are Windows and Linux. So, they have got this one to one model. So, whenever a user level thread is created, a kernel level thread is also created, and there is an upper bound on the number of threads that you can create in a process. So, that is one to one model. Then there can be many to one model. So, many to one model, so many user level threads mapped to a single kernel thread. So, we have got a single kernel thread here. So, many of these user level threads, so they are mapped here. Similarly, there can be another set of user level threads, so they are mapped to another kernel thread. So, I can have mapping, but this mapping is fixed. So, if this thread is blocked somehow, maybe this fellow has made a system call and it was getting executed by this kernel thread, and it got blocked somewhere here, then these threads will also get blocked because they cannot make any system call. Of course, this group does not suffer because of this thread getting blocked. So, this group does not suffer. So, we have got this many user level threads mapped to a single kernel thread, and one thread blocking causes all to block. So, that is the thing that I was telling, that if this thread gets blocked, then all these threads they will get blocked. Multiple threads may not run in parallel on multi-core system because only one may be in kernel mode at a time. So, this is another difficult situation. What it says is that so maybe I have got multiple cores. Now, this multiple cores, suppose I do not have this thing, I do not have this second one, I have got only these 4 user level threads, and this is a kernel level thread. And now, suppose I have got 4 cores in my system. So, I have got 4 cores. So, they are this is given to core C1, this is to C2, this is C3, and this is C4. But after that C1 has made a system call and it is here. Then if C2 in its execution also needs to make a system call, maybe C1 wants to print something, and so it has made a call to printf, and as a result it has gone into kernel mode. Now, C2 also, this is for C1, and C2 also wants to print something. C2 wants to maybe may not be printing. So, it may be opening a file, it may be open a file, but now this thread cannot proceed because only one kernel thread was there for this C1, C2, C3, C4 group of user threads, and that is now busy with C1's system call. So, C2 has to wait. So, even if you have got multiple cores available, so you cannot make them to run parallelly. So, multiple threads they may not run in parallel on multi-core system because only one may be in kernel mode at a time. And few systems currently use this model, like Solaris green threads, GNU portable threads. So, they follow this particular strategy. The advantage that we have is, of course, the mapping is unique. So, that way the handling this kernel mode of operation becomes simple. So, that is why it is done. So, maybe it will work well for many systems, and that way we can use it. Another model that we have is the many to many model. So, this is a more flexible one that way. So, we have got a group of kernel threads, and we have got a group of kernel threads like this, and we have got a group of user level threads, and the mapping is between them. So, whenever this user level thread, so this user thread, suppose it wants to make a system call. So, the system will find out whether any kernel level thread is free, maybe this one is free. So, as a result this system call will be executed by this thread. Now, unlike the previous one where we had got a single kernel thread for a group of user threads. So, here I have got multiple kernel threads. So, if this fellow now makes a system call, then maybe it can find this thread that can take it up. So, there is no distinction between the capabilities of this kernel thread. So, when they all of them can execute, all of them can realize all the system calls. So, as a result there is no distinction between their capabilities. So, only thing is that they should be free. So, if the kernel thread is free and any user thread makes a system call, so it will be taken up by that. So, it allows many user level threads to be mapped to many kernel threads and allows the operating system to create a sufficient number of kernel threads. So, now the OS designer is now a bit safe, because unlike that one to one mapping, when that is whenever a user thread is created, so one kernel thread will be created. So, like that, or say that fixed mapping, that many to one mapping, like only one kernel thread is there for a group of user threads. So, that type of situation. So, what happens here is that the OS designer can decide, okay, I will create some number of kernel threads which is assumed to be good enough for the type of load that the system has, and it may also be a tunable parameter that way. So, that way, so the user the OS designer will create a number of kernel threads and then do this mapping between the user threads and kernel threads. So, allows the operating system to create sufficient number of kernel threads, and Solaris prior to version 9. So, it was using that. So, Windows with thread fiber package. So, this can also be that they also use this type of facility in which this can be implemented. There can be another situation which is known as two level model. So, it is similar to many to many, except that it allows a user thread to be bound to kernel thread. So, this is many to many. So, we have got here we have got this many of these user threads. So, they are bound to some kernel threads, but the set that is bound to, so that is fixed. So, this set of user threads it is bound to the kernel thread. Similarly, this set is bound to, so this thread. So, that way it goes on. So, the typical examples of this type of system is IRIX, then HPUX, then True64 Unix and Solaris 8 and earlier systems. So, they use this two level model. So, many to many model is the most generic one. So, that is there. So, that it is there, but this two level model. So, it allows a user thread to be bound to the kernel thread. So, their binding is fixed. Now, going to thread libraries. So, there are different libraries that have been created for helping the user to write programs using the using this threading philosophy. So, otherwise it is difficult to develop applications around thread using this thread concept. This thread library, it provides the programmer with an application API interface for creating and managing threads. There are two primary ways of implementation. One is library entirely in the user space, and we can have kernel level libraries supported by the operating system. So, as we know that there are user level threads and kernel level threads. So, it may be that we can have this library entirely created in the user space. So, all the libraries that we have, so the user level thread will be using it, and of course, the operating system will support this kernel level thread. So, that can be utilized. So, there are three primary thread libraries. One is the POSIX pthreads library, then we have got Windows threads library, and we have got Java threads library. So, all these libraries, they will provide us some way by which we can create some threads, we can do computation, we can do waiting for some thread to be over. This parallelism can be taken care of. So, we will be looking into these thread libraries. So, the one of them is this pthreads library, and it is provided as a standard. So, it has become a standard now. So, many of the operating systems you will see that they will follow this these pthreads libraries like Solaris, Linux, Mac OS X and all. So, they support this pthreads library. So, we will not go into much detail of this pthreads, but we will try to get a glimpse of like how these thread level programs will look like. So, that we will do. in the next lecture.